So here you see that looks like a continuous transition. If you're not quite sure from this plot, here's the inverse susceptibility, the magnetic susceptibility, plotted against 10% to the 4/3, against the bias by theory, that 4/3 exponent. And you see the inverse susceptibility actually very nicely goes to 0 here. So the susceptibility seems to diverge, hallmark of backborder transition. And here's some more evidence for that, where the square of the magnetization is plotted against 10% to the 4/3, and again, things seem to go to 0 in a continuous way. Okay, so that's actually that's a very nice and complete experimental paper that maps out this backborder transition. And this order, like I said, it does other things in addition to suppressing the cyclical points and the rings. And so here are the two examples. Here's another one of these uranium compounds. That's one where you can substitute thorium for uranium, and that introduces this order. Nasty stuff, but some people do that. And as a function of the thorium concentration, you see again CC marches down, then it develops this interesting tail here, and there's interesting stuff related to Griffith's physics believed to be going on in this tail. And the reason that's believed to be the case is that one sees very unusual behavior of the magnetization as a function of the magnetic field, for instance. But I won't go into the details of this. Okay, and finally, let me mention something that I will not dwell on in these lectures, but it's still very interesting. So for the point of this overview, I wanted to mention it. In many of these materials, there is weird transport behavior observed in large parts of the baseline. So an ordinary metal that is described by Fermi-Liquid theory has a resistivity, an electrical resistivity that goes like the temperature squared at low temperatures. And here is for its color plot for zirconium zinc 2 again, where the color indicates the exponent, the temperature exponent of the electrical resistivity at low temperatures. So 2 is somewhere here between blue and green, and the darker blue it is, the lower is the exponent. So the darkest blue is something like 3/2. And so here is the ferromagnetic phase, here's the paramagnetic phase. That's the same phase that we looked at before, this one here. And as you can see, the exponent is substantially less than the Fermi-Liquid value in a huge temperature pressure region. Okay. So up here, it behaves like it's supposed to, being a level, but here it doesn't. And you might say, well, there's a kind of phase transition going on, so no wonder the transport looks weird. Somehow, that explained explanation doesn't quite cut it. Because if you look at the numbers here, so here's the critical pressure, 1.6, 1.7 gigapascal something, and you see that the anomalous exponent is still observed at 2 times the critical pressure. Okay. So whatever's causing it can possibly have much to do with this one phase transition. That's just way too small a thing. And here is a plot, a more direct plot of the resistivity normalized to something versus temperature to the 3/2, and you see a pretty nice straight line. So there is a T to the 3/2 law for the electrical resistivity in large regions, and that's again not confined to zirconium zinc 2, plenty other materials do that too. And while there are something between 5 and 7 explanations for this floating around in the literature, there's actually no consensus as to where that's coming from. So it's an interesting open problem. So that's just a rough overview of some of the phenomenology that's behind what I want to talk about. And in collaboration with Manuel Brando at Princeton and Malte Grosch at Cambridge, we just wrote a review article about this actually, so you can find it on the archive, and it will come out in the News of Modern Physics sometime this year. For the information. Okay, so any questions at this point? Yes. Okay, so the question is whether there are other indications of non-Fermi-Liquid behavior in these data in the case of the phase diagram other than the transport. That has not been looked at in detail for zirconium zinc 2. The thing about the resistivity is that it's easy to measure, of course. So somebody, I forget who, once said that the resistivity is always the first thing to be measured and the last thing to be understood. So for zirconium zinc 2, I think the answer is no. But for instance, in MNSI, people have looked at by means of neutron scattering in more detail at what happens to the magnetism, for instance. And so what they found is that concurrent with this T2-3/2 behavior, there are also weird things happening to the magnetic spiral. So for instance, the direction of the pitch vector changes, And in the paramagnetic region, of course, there is no there's no long range order anymore, but it's a short range spiral order that's oriented in a different way. And that's also not completely understood. So there's a lot to be done, I would say, in that area, both experimentally and theoretically. Anything else at this point? Again, please interrupt me anytime. Okay? Good. So, then let's see whether we can understand why that is. So what I essentially want to do is explain where this type of phase diagram is coming from, what's the physics behind it, why it's so universally observed in clean metals, and why it's observed only at low temperatures, and why it doesn't like quench difference. So these are the main questions that we are trying to answer. And in order to do so, let's go back quite a bit and just review a few very basic properties of ferromagnetic phase transitions. So let's talk, before we talk about quantum ferromagnets, let's talk about classical ones for a while. So of course, the ferromagnetic phase transition is one of the best known examples of very continuous or second order phase transitions due to iron, nickel, and cobalt. It's been known since ancient times. And here you see, for instance, the historic experiment by Pierre Weiss on nickel, where they measured the magnetization versus the temperature, and they found it goes down and follows approximately a square root. And here's the schematic phase diagram, so magnetic field versus temperature. Here's the Curie temperature, here is the ferromagnet, here is the polarized, here are the polarized phases, and what the experiment does here is it comes down in temperature at zero field straight towards the crystal. And here's the magnetization versus temperature schematically. And the solid line here actually is Weiss's very own mean field theory. So somebody asked yesterday when we were meeting with the students whether it's possible to do both theory and experiment at the same time. Pierre Weiss was still able to do it, but that was a long time ago. That was 90 years ago. So these days it's much harder because things have become so much more specialized. Cool. So for our purposes, this transition is second order, i.e. the magnetization, which is our order parameter, goes to zero continuously. There's no latent heat, and it's one of the transitions that look pretty weird to people than Erland initially classified transitions as the first and second order. Whereas if you go to a temperature below the Curie temperature, let's say you're at room temperature, and you trigger the transition from the spin up phase to the spin down phase by means of a magnetic field, that's a classic example of a first order transition. So the magnetization just jumps discontinuously at zero field, and then there's complications due to domains and so on and so forth. But to zero approximation, that's what it does. So that's a classic example of a thermal ferromagnetic phase. Now, as time went by, and so Pierre Weiss, of course, was quite pleased to see that his theory, which predicted a square root, fit his data pretty well. Now, as time went by, people got interested in these continuous phase transitions and studied the region close to the transition in more detail. So they did more and more precise experiments closer and closer to the Curie temperature. That turned out to be difficult and require a lot of time and experimental skill. And while doing that, they lost their theoretical skills and vice versa. So then in 1977, let me just advertise my late friend Dave Cohen's thesis. For his thesis in 1977, he measured the exponent beta in nickel. So beta is the thing that tells you how the magnetization goes to zero at the Curie temperature. And actually, almost 40 years later, this value for beta, 0.358 plus minus 0.003, is still the accepted value of beta in Heisenberg ferromagnet. That's quite an impressive thesis. And here you see again the Weiss plot. The conclusion was that if you look into the shaded region here close to CC, then you start seeing deviations from Weiss theory, and the exponent is actually markedly different from 1/2 at the end of the day. So, why is that? What's wrong with Weiss theory? Now, Weiss, of course, considered an effective medium theory, or what we call a near field theory now, where he said, let's look at one thing, let's say, in the average field that's produced by all of the other things, okay? And ignore fluctuations of the magnetization. If you do that, then you find this exponent 1/2. but the magnetization does fluctuate, and fluctuations get bigger and bigger as you get closer to DC. So as a result of that, you eventually find these deviations. Turns out, actually, that that's true in 3 dimensions. But if we could do experiments in, let's say, 5, 6, or 17 spatial dimensions, then a ferromagnet in such a high-dimensional space, we have every reason to believe would strictly follow right here. The exponent would actually be 1 half. And whether or not the fluctuations are small enough to lead to deviations from mean field theory, that's known as the Kirchhoff criterion, I will come back to that later. And so in the case of these magnets, there's a critical dimension that equals 4. So if you are above that, then mean field theory works. If you are below that, then it doesn't. And that concept will become important in what follows. Turns out 4 is the upper critical dimension only for this certain class of magnets here, and we'll encounter other cases later. Now, the magnetization is only one observable that shows interesting behavior. So other stuff that you can measure that shows critical behavior is the susceptibility, of course. So the susceptibility diverges with an exponent that's usually denoted by gamma, and turns out in these Heisenberg ferromagnets, gamma is roughly 1.4. And the theoretically probably most important property here is the correlation length, which tells you that if you have a magnetization fluctuation at one point in space and a magnetization fluctuation at another point in space, to what extent these fluctuations can see each other. So if you look at the correlation function of the magnetization, then that falls off on a spatial scale given by the correlation length, and that thing diverges with an exponent that's usually called mu, and it is close to 0.7 for each iteration. Now, the values of these exponents turn out to depend only on a few basic properties of the system. Spatial dimensionality is one of them. Dimensionality of the order parameter is another one. They're different for Heisenberg ferromagnets and Ising ferromagnets, for instance. They do not depend on macroscopic details like crystal structure, band structure, and so on. If you look at iron, nickel, cobalt, they all have the same critical exponents, even though they are quite different in microscopic detail. And so the broad classes of materials that all have the same critical behavior are known as universality classes. So iron, nickel, and cobalt belong to the same universality class. And these observations of critical behavior that's not mean field-like, that spawned a huge theoretical development in the 1970s. So Ken Wilson, of course, won the Nobel Prize for that, and that led to the development of the randomization group and scaling and all of that. Scaling historically came earlier, but then the randomization group allowed us to actually derive scaling. So here's an example of scaling behavior. Let's say we look at the magnetization as a function of distance from criticality and temperature space and magnetic field. So little t here is, let's say, the dimensionless distance from the cubic temperature. And as a function of these two variables, it turns out the magnetization close to the critical point is only a function of a particular combination of the two variables. It's not an independent function of the two variables. And here's one way to write it. One can write it as little t to the beta, so that's the critical exponent we had a second ago, and then times the function of the magnetic field over little t to another exponent only, rather than a function of h and t separately. And that other exponent turns out to be the product of two critical exponents. One is theta and one is delta. Delta is the one that tells you how the magnetization varies at criticality as a function of the magnetic field. So what scaling predicts is that if you look at, for instance, a plot of magnetization versus field, or field versus magnetization, then you see for temperatures higher than the Curie temperature, the magnetization increases as a function from 0 as a function of field. For temperatures below the Curie temperature, what happens is that in zero field, the magnetization is non-zero, plus or minus, depending on the value of whether the field is plus or minus. And then it still increases, of course, as a function of field, but you get this whole set of curves here that fill your HM space. And what scaling says is if you plot the correct combination of things here, then these curves will all collapse onto two curves. One for all temperatures below TC and one for all temperatures above TC. That's the visual message that's given by the scaling law. So if you take m, divide by t to the beta, then the result will be a function only of this combination. That actually works. So here is an example. This is an insulating magnet, but it doesn't matter for this purpose. And here you see people have done literally what I just described, and here you see the data points, these whole families of curves all collapse onto two curves, one for t less than tc and one for t greater than tc. And these curves were produced long before the randomization group was developed, and they were actually important in guiding the theory along. So scaling theory was a phenomenological development before the randomization group. I lost track of the situation. That's the wrong one. Okay. Another point I want to make, because I need that later on, is that the randomization group is actually much more useful than just describing critical points and phase transitions. And that's something that's not as well appreciated as its utility for critical points. So it turns out one can use it to describe entire phases. There's a randomization group 6 point, for instance, that describes the ferromagnetic phase. And another one that describes the paramagnetic phase. So these are called stable 6 points as opposed to critical 6 points. And I'll come back to that later on when we talk about ferroliquids and what they do in conjunction with metallic magnets. And that issue is, for instance, discussed in the book by Shantang Ma, which is like this. So, now, how can we theoretically deal with these issues? How do we describe this kind of stuff? It's done by means of field theory. So one looks at what's usually called an action, which is really a Hamiltonian divided by temperature. That's a functional of an appropriate order parameter field. So in our case, if we're interested in magnets, then the order parameter field would be the magnetization. For thermal position, it's magnetization as a function of spatial position. And here is a simple model functional. So let's say it should have a quadratically ordered parameter. Inhomogeneity is the order parameter we call density. So let's put in a term that depends on the gradient of the magnetization squared. And then there will be a quadratic term, there will be higher order terms that turn out not to be important. And let's couple the magnetic field to our magnetization by means of a Zeeman term. So if this is supposed to be the Hamiltonian normalized by temperature, then the Zeeman term will come with a minus sign. Okay, minus h sub m. And the coefficients here, delta c, and u, they're the parameters of this theory that's usually referred to as the Landau-Gibbs-Progressive theory. And the partition function we obtain as a functional integral over all possible configurations of the spatially dependent magnetization. So it's like a path integral in quantum mechanics. What you do is you take a particular magnetization configuration, you calculate the action, you exponentiate it, then you take a different magnetization configuration, do the same thing, you add all these things up. Okay? What comes out is your partition function. And once you know the partition function, of course you know all of the thermodynamic properties of the system. In particular, all of this complicated critical behavior is actually contained in this quantity C. So that by itself tells us that it can be easy to calculate. To get an idea of what might happen, let's do a very simple approximation. Let's do what Pierre Weiss did and just ignore fluctuations of magnetization. Let's say the thing is a constant. It's independent of position, so it's equal to an... And what will happen is by some way or another, we manage to suppress the Curie temperature and look at materials that order ferromagnetically only at rather low temperatures. Let's say a few Kelvin or maybe a few tens of Kelvin. And we could do that by either finding materials that have a low Curie temperature to start with, or we might also find some way to suppress the Curie temperature of material that we found. And there are actually several ways to do that. So here is one example. The common zinc 2 is a ferromagnet below a temperature of some 28 degrees Kelvin or so. And it turns out that if you subject the material to 100